Welcome to the next part of the module, which covers the Java CountDownLatch class that implements barrier synchronization. This part provides a conceptual overview of barrier synchronization, explains how the Java CountDownLatch class implements these concepts to enable one or more threads to wait until a set of operations being performed in other threads completes, and shows how countdown latches are applied in Android. A barrier is a synchronization technique that halts the progress of one or more threads at a particular point. No thread can proceed until all other threads reach this barrier, as described at this link. Barriers are commonly used in several ways. One way is to defer the start of concurrent computations until after an object has been initialized. For example, the main thread of an application that converts a video from AVC HD format into MP4 format might spawn 4 threads to run different parts of the conversion computations on different cores. An initialization done barrier, created with a count of 1, can be used to defer the start of these threads until the main thread has finished initializing its internal data structures. When initialization is finished, the main thread decrements the count to 0, and all the threads can begin their conversions concurrently. Another common use is to allow one thread to wait until a group of other concurrent threads are done with their processing before it can continue. For example, the main thread in our video format conversion application can use a conversion done barrier created with a count of 4 to wait until all the threads finish their conversions before continuing with its other work. As each thread finishes, the barrier count is decremented by 1. When the count reaches 0, the main thread can continue. A human-known use of barrier synchronization is the protocol used by a tour guide, described at this link, who waits until all the tourists have arrived before starting their tour, and who also waits until all the tourists have finished the tour before continuing with their other work. Java provides barrier synchronization via its CountDownLatch class, which allows one or more threads to wait until a set of operations being performed in other threads have completed, as described at this link. Most of its implementation is written in Java, as shown at this path name. CountDownLatch uses the Gang of 4 bridge pattern, described at this link, to inherit the bulk of its functionality from the abstract queued synchronizer class, which provides a framework for implementing blocking locks and synchronizers that rely on first in, first out, or FIFO wait queues, as described at this link. The constructor initializes CountDownLatch with a given count. Once this count is set, it can't be reset without creating a new CountDownLatch instance. An alternative is to use a Java cyclic barrier, which is cyclic because it can be reused by resetting the count after waiting threads are released. Cyclic barrier is useful for programs with a fixed size number of threads that wait for each other, as described at this link. The key methods in CountDownLatch are await and countdown. Await causes the calling thread to wait until the latch's count reaches 0. Countdown decrements the count of the latch, releasing all the waiting threads if the count reaches 0. A countdown latch doesn't require that threads calling countdown wait for the count to reach 0 before proceeding. It simply prevents any thread from proceeding past an await call until all threads can pass. To show how Java countdown latches are used in Android, we'll analyze its contacts provider, which is a source of data for a device's contacts application, as shown at this link. The contacts provider is implemented by the contacts provider 2 class, which extends abstract contacts provider that in turn extends content provider, as shown at this path name. We don't analyze every detail of this code, just the parts we need to explain how countdown latches work. A content provider is a core Android component that manages access to a central repository of structured data, as described at this link. The contacts provider presents its data to applications via standard content provider methods, such as insert, query, update, and delete, which internally access multiple SQLite database tables. A pair of countdown latches are used to defer read and write operations until the contacts provider is properly initialized. The contacts provider onCreateEntryPoint method calls its internal initialize method. Initialize starts a background thread that initializes the SQLite database by importing the legacy contacts, updating accounts, locale, and search information, etc. These time-consuming tasks continue to run concurrently even after initialize and onCreate have returned. So contacts provider methods, such as query and insert, must not be allowed to read from or write to the database, since its state will be inconsistent until the background initialization tasks finish. To ensure consistency and to optimize performance, 2 countdown latches, each initialized with a count of 1, prevent database access during initialization. Splitting the countdown latches into read and write access optimizes performance, since read-only methods on the contacts provider can be processed as soon as that portion of the database is initialized. For example, any calls to query block until the read access latch count equals 0. Likewise, any calls to insert block until the write access latch count equals 0. All these contacts provider methods called the private wait for access method, which calls a wait on its countdown latch parameter to block the caller until the designated initialization is complete. As initialization tasks running concurrently in the background thread complete, the perform background task method calls countdown on the appropriate read and write access latches, which unblock any methods that read from or write to the contacts provider so they can proceed and compete for the database transaction monitor. In summary, a Java countdown latch provides a versatile barrier synchronization tool that can be used for several purposes. If it's initialized with a count of 1, it serves as a simple on-off latch. For example, in our earlier video conversion example, all 4 threads that evoke await block on the initialization done latch until the main thread invokes countdown. If it's initialized to n, it can make one thread wait until n threads have completed some action or some action has been completed n times. For example, the main thread in the video conversion example waits until all the worker threads are finished, at which point it returns to its caller. A countdown latch supports several types of await operations, including an await that causes the current thread to wait until the latch is counted down to 0, unless the thread is interrupted, or a timed await that blocks until the specified waiting time elapses. Countdown latch is used throughout Android, both in its frameworks and in its common applications and providers.